everyone, welcome back to 3 Deviations. So in this video we're kind of going to be starting what is typically Calculus 2. So we finished the substitution rule in the last video, and now we're going to be switching to our new unit, which is applications of integration. So we're going to be covering the applications of the very, very basic integration ideas that we learned back in Unit 4. So the plan for Calculus 2 is that we're going to have this unit on applications of integration. Then we're going to learn some more advanced techniques of how to integrate functions that go beyond the substitution rule and the elementary techniques. And then we'll cover some applications with those newer techniques. And it's going to be the first third, or the first half maybe, of Calculus 2. So it's going to be taking up a fair amount of time. But today we're going to be introducing a topic in Calculus 2, which is areas between curves. So this is one of the first applications that we have. So originally we talked about finding the area between a curve and the x-axis, right? So we'd integrate a function between 2 points on the x-axis, and we'd find the area under the curve between the curve and the x-axis. Well, in this part, we are going to be, instead of using the x-axis as a baseline, we're going to use another curve as the baseline. So we'll be able to find the areas between curves. So why don't we define this first? So about this, we have our just simple area approximation here, which is the just our little sum here. So we have our Riemann sum here, so we have our area is approximately going to be the sum from I equals 1 to n of f of x sub I, so our top curve, minus g of x sub I, which is our lower curve, and that's with a delta x. So it's very similar to what we did in the past. It's just that we are having a subtraction, and we know how to subtract integrals. We can just take them together or take them apart, however you'd like to do it. So as you know, what we do with this is we'd attach our limit, right? So we'd have our area is now equal, definitively equal to the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I minus g of x sub I times our little change in x. And of course, as we know, this goes to an integral where we have a as the integral from a to b of f of x minus g of x dx. All right, so why don't we try an example with this? So we're going to have two types of examples for finding areas between curves. The first is an easier example. The next type we'll cover later. That's a little bit more tricky. So for this example, we're going to be given our endpoint. So we know we're finding the area between x squared and x from 1 to 2. So this is easy because we have our endpoints. What the other type of example would say is it would say find the area between these two parabolas, but we don't know what the endpoints are. So the hardest part of the problem in that case would become finding our endpoints. What are we integrating from? So we need to find the intersections of those parabolas in order to construct an accurate integration. But now we are just given our endpoints here, and we're just going to be finding the area between these curves from 1 to 2. So this is going to be easy. We're going to set up our integral first. So we're going from 1 to 2, and we have our functions x squared and x. So we're going to put x squared as the top function. We're going to subtract x from it. So this is how it works. We're doing our f of x minus our g of x with respect to x. If I wanted to, I could separate these integrals and do them separately, but we can do this together because we know our integral properties. So as we know, these are simple power functions, so it will just take us to 1/3 x cubed minus 1/2 x squared. It's the power rule there, and we're evaluating that between 1 and 2. All right, so now comes the tedious part in my opinion, unless if you have a calculator, but that gives us 1/3 times 2 cubed minus 1/2 times 2 squared, and then minus 1/3 times 1 minus 1/2 times 1. And that's we don't even need to put the cubes and squares there because we know where one goes when it's cubed and squared. And that becomes 5/6 once you do the math out. So that is how we find areas between curves in a basic way. So you can imagine how this would get harder. We chose really easy functions, x squared and x, really easy to integrate, but we could have some harder functions in there. And this is going to be something that's going to apply all the way through our study of integration. And then again, we have other examples where we will have to find the bounds, and that's almost something that comes up a lot in multivariable calculus when we integrate over volumes. All right, so we hope that you enjoyed this video. We hoped it helped. It gave some intuition. And in the next video, we're going to do a couple more examples of this with some more tricky functions. And then we'll start with the examples where we need to determine our bounds of integration. And that's going to be a nice beginning to Unit 5. All right, thank you.